it is physics.
What is makeup?
Yay!
Okay, so
There we go.
All right. Let's get started, please. We can get through this. For the first part of class today, on Wednesday of this week, we talked about how to name compounds and how to write the formula for compounds that are held together by covalent bonds and then formulas that have polyatomic ions in them. By the end of class on Wednesday, a lot of you were pretty solid with it, but I'm assuming none of you really looked at it since then. We need to practice this a little bit more. So, for the beginning part of class today, I put together just a couple of examples. I'm going to give you, on the board, I'm going to give you some formulas, or I'm going to give you a name, and you're going to have to come up with the formula. This is not a turn-in thing. This is something for you to practice. So if you want to get like a separate sheet of paper, if you want to do it on the back of something, but this is definitely going to be something that is going to be good practice as we go forward. So grab something to write on, grab something to write with. You probably need your periodic table. If you have some notes from the other day that you want to maybe look at, that might be a good idea too. All right, number one, and here we go. Here are two formulas. Write me the name of these compounds. You can talk to the person next to you if you need to bounce some things off, make sure you're doing things correctly. So here are two formulas. Write me the names of these compounds.
I just know that.
You have to figure out how to make the names. Part of this exercise.
Wait, there's a number. It's like lithium iodide.
Mono. It's on the back. Mono iodide. That sounds so bad. Yeah, because I think so. It's like right That's AO.
Oh, that's an L. Aluminum trifluoride.
Right? Well, that's right.
All right. Let's discuss. So, the first thing that we talked about on Wednesday is that there are different rules for naming compounds that have ionic bonds in them and different rules for compounds that have covalent bonds in them. So the first thing you have to do is you have to identify whether this is a compound that has ionic bonds or a compound that has covalent bonds. So looking at the formula for this compound, is this going to be an ionically bonded compound or a covalently bonded compound? This is an ionic bonded compound. And we know that because what kind of elements does it have in it? It's got a metal and it's got a nonmetal. When we name ionic compounds, we said the name is based on the elements that are in it. First part of the name deals with the cation, which is the metal. So the first here we're going to write lithium. And then the second part of the name deals with the nonmetal part, iodide. No prefixes for this one. No prefixes here because what? It's not a covalent bond. There's only, Omar, there's only one possibility for a compound between lithium and iodine, and it has to be this, based on how many electrons lithium is looking to lose and how many iodine is looking to gain, blah, 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 right? So we don't have to worry about the prefixes there because there is no other combination of lithium and iodine. And that same thing goes here for number 3. So this would be aluminum fluoride. Oh. Aluminum fluoride.
So there's not the tri.
Nope, because it's not a covalent bond. All right, next screen. Next screen. Here are 2 names. Write me the formulas that go along with these names. Here are the names of 2 compounds. Write me the formulas that go along with those names. Here are 2 names. Write me the formulas.
Yes. On sodium phosphate phosphide.
Oh, barium is charged there. Yeah. Okay, so then this will be
7 is what? All right. So, to get the formula for this compound, you don't necessarily have to show me all of this work, but we know that this is an ionic compound again because it has a metal and a nonmetal in it. So, you go to the periodic table and you find these elements. So we find barium. Dudley, you found barium before, right?
Yeah.
Barium is in which group?
Alkali earth metals.
And that's which number group on the periodic table?
2.
It's group 2, meaning that it has what?
2 valence electrons.
2 valence electrons. Duffy, what is it going to do with those 2 valence electrons?
Try to lose them.
Try to lose them and form what kind of an ion?
Cation.
Cation. And what charge is that cation going to have?
Positive.
Positive 2, right? Because it's going to lose both of those valence electrons. So you find barium on the periodic table, and you see that it's going to form this ion. Chlorine. Where does chlorine show up on the periodic table? Group 17, right? But that means it has what?
7 valence electrons.
7 valence electrons, right? Eric, what is chlorine looking to do here if it has 7 valence electrons?
Is looking to
Gain 1, and it's going to form what kind of an ion?
anion.
Anion. What's its charge going to be?
-1.
Okay. All right. So now, to form the compound, right, we have to balance out the positives and negatives. Least common multiple between these charges is what? 2. So to get to 2 positive charges, we only need 1 barium. But to get to 2 negative charges, how many chlorines do we need? 2. So formula BaCl2. All right. Going through that same process, you'd end up with this formula for sodium phosphide. Good there?
See, even it wants us to do it.
Say again?
Even it wants us to do it.
Go ahead, just put your head down, Kevin.
Wait, we're laughing at this class?
You're still going to be tested on this, but you can nap all you want.
Okay.
I mean,
Katerina, what? Katerina looks bad.
all right, next. 2 more names. Write me the formulas for these compounds. 2 more names. Write me the formulas for these compounds.
That's
I lose our time when I walk upstairs because I'm gonna be so slow because I have to take my class on stuff.
wait, why are you? Oh my god.
Do that.
That looks like I did all that. You're probably right. That's
Christine, it only matters when you take the
Got it.
test, right?
Just saying.
yeah.
Do I have to take a quiz on Monday? Or do I usually
Probably not.
go into your classroom? Oh shit.
All right.
Quiz.
Any questions about these two?
No.
So now we have changed. Now we have changed the rules, right? We're dealing with a covalent compound now because we have only nonmetals, and that's where we have to start looking at using the prefixes. Next, here are two formulas. Write me the names of these compounds. Here are two formulas. Write me the names of these compounds. Oh, sorry. Hold on.
We're not using nickel.
Hold on.
Nice nickel.
Typo.
Typo.
Nickel.
I forgot to change this before.
Yeah, I was right.
What? Why is
Two
that?
nickel. That makes a little more sense. Where's silicon?
So it's silicon?
Oh my god.
No, it's tetra. Tetrachloride.
Tetra is full.
Yeah.
You guys, I don't have to go to classes upstairs today.
Why?
Because they're like liable if I find out.
Really?
Oh yeah, because the elevator.
Wait, so what? So you don't need to go to Spanish?
Awesome, that's what psychology geometry.
What
What are the first two upstairs? That's it.
What are you gonna do? Just chill somewhere?
Yeah, you have to go to like the guidance office.
Wait, there's two. So that's not fair. Can I break my leg? Can I seriously? I don't want to go to
Katarina's not.
Spanish.
Katarina's not Tetra. She's still going to class.
Why? I already put that in my locker though. What? I already put my crutches in my locker. Wait, where are you're not using your crutches?
I just want to go to.
Then I love my hair.
No, like I was like, oh, can I still go?
All right.
And then she's like, no.
Answers up on the board. Any questions there? All right. Next. I'm assuming the next two slides are going to be more difficult than the ones we've done up until this point. Here's the first one. There are two compounds, two formulas down at the bottom. Up at the top, those are our polyatomic ions. You don't have to memorize them, right? But there they are for you. So, there are the two formulas. Write me the names of those compounds. There are the two formulas. Write me the names of those compounds.
What does that chart do?
Mr. Plants, like, can you describe
I think it's
I don't. I feel like I describe it all wrong.
This is a tough one.
Where's N?
So wait, I don't.
How is this different from the other one?
I don't even
Talk about
know.
that.
Mr. Planus, there you go. What does CO stand for? Cobalt.
Sodium.
Well, it's not CO. But, oh yeah, cobalt can be a C. Lowercase o.
Is that really what it is? No.
Disodium
I'm not
carbonate.
gonna write anything down.
My stomach hurts so bad. It hurts so bad.
What?
Disodium
Yeah,
carbonate.
it's just
Is it tetrasodide?
no.
Sodiide?
That's exactly. It's okay. It's okay to not know it.
Nobody loves me.
Okay.
You can look at your book too. In your notes from Friday or from Wednesday, you have the short book.
Like I thought I did, but I don't.
I can see it.
You can sit
Wait, is
close to
this
the
it?
front.
Wait, no. Do me one more time. I think I remember how to do this. So NA2.
So you think sitting in the back corner and talking is going to be better than sitting in the front corner and talking?
This is not bothering me.
Wait, that.
All right,
Wait,
let's
okay.
discuss. So, talked about the idea.
Wait, I think.
So on Wednesday, we talked about the idea of a polyatomic ion. We said that this group right here, CO3, is 1 carbon and 3 oxygens. Those one carbon and 3 oxygens come together and they share electrons. They are covalently bonded. But there isn't enough electrons there for everybody to have stable 8s. So they need to pick up some electrons from somewhere else. That's why it has the -2 charge. But because the carbon and the 3 oxygens are bonded together, they act like a group. And we call that group a polyatomic ion. Once it forms the covalently bonded polyatomic ion, it attracts other positive ions. So this is actually an ionic compound, even though it has covalent bonds within it. That being said, the name of an ionic compound is just the name of the name of the cation and the name of the anion. So the name of this is sodium carbonate. You do not change the name, or you do not change the ending of the name on the polyatomic ion. It's carbonate here, it's carbonate here. Okay? Catherine, go ahead.
Why is it not disodium?
Because this is an ionic compound. There is only one combination that forms between sodium and carbonate. And it's that ratio.
What is the 2 for?
The 2 is relating to the sodium, just like, oh, too far. Just like this 2 relates to chlorine, right? But we don't call this barium dichloride because there's only one possibility for the way that barium and chlorine can come together, that all of them have 8 valence electrons. Same thing here. There's only one possibility for sodium and carbonate, that group of atoms that we call carbonate. 2 sodiums have to balance out 1 carbonate ion.
So with a polyatomic ion, you don't use the numbers?
No, because it's an ionic compound, even though there are some covalent bonds in it. All right?
You're giving us that thing, right?
This chart I will give you on the test. Okay? Then here, this is magnesium sulfate. It's sulfate in the chart. It's sulfate here. You don't change the name of the ending. Okay? But it's just the 2 names. Okay? Good there? Last one. Here are 2 names. Give me the formulas for those compounds. Here are 2 names. Give me the formulas for those compounds.
We're sorting, like, we did like 10 minutes of singing on songs.
Do we have to come into that class during midterm week?
No, a midterms this
We get to
next block.
No, you said we were gonna have it.
He said on Wednesday.
I got the first one right.
He said on Wednesday, like
This
on
Wednesday?
Yeah.
What's
during
your
block.
midterm?
Like symbols,
Fake.
test, right?
All right.
So it's not like that kind of question.
There. So there are formulas for these two compounds. Hydroxide, if we look on the table, right, hydroxide has a -1 charge on it, but the magnesium has a +2 charge based on its location on the periodic table. Therefore, we need 2 of those hydroxide groups. That's where we have to use the parentheses to show that we need 2 of them, right? Then for the sodium sulfate, sulfate comes with a -2 charge. Sodium comes with a +1 charge, right? Good there. Okay, so we did some practice with this today. We will practice again on another day next week, maybe Wednesday next week. You are going to see this on your test, I'm telling you, right? It's going to show up on the test. So make sure you're taking a look at these things. If you need some more practice, there's some practice things in your book. Look at the homework assignments that I gave you over the past couple of days. If you need more practice than that, I can give you a couple other sheets if you need to practice a little bit more, but you're going to see it again. Zoe, go ahead. Prefixes for naming covalent compounds will be on the test. The chart will be on the test. And then I will also give you, like, this chart, the chart that has the polyatomic ions on it as well. Okay. Yep. Objective sheet I will get posted today, and so you'll have it for the weekend. All right, let's put that away, and let's pull out outline dealing with covalent bonds. Outline dealing with covalent bonds, which I apparently have.
Although I rocked at my makeup skill test today.
All right. Hey, that took a lot longer than it was supposed to. So now we have to do this kind of fast. So all the little chit chat has to stop. Okay. All right. On Tuesday, we started talking about covalent bonds. We said that covalent bonding is another way that atoms go about forming that stable octet, forming that 8 valence electrons. But we said it's different in that it is quote-unquote electron sharing. At the end of the period on Tuesday, we talked about that covalent bonds are going to be formed between 2 nonmetals, whereas ionic bonds form between a metal and a nonmetal. Because if you're going to share electrons, both atoms have to want those electrons. So it has to be 2 nonmetals to form the covalent bond. We talked about that a covalent bond is always a pair of electrons. Atoms don't share a single electron, they share pairs of electrons. So they can share just one pair of electrons, and we call that a single covalent bond. Or we could have situations where atoms will share more than one pair of electrons, and we call that a multiple covalent bond, either a double or a triple. Double bonds being 2 pairs of electrons, triple bonds being 3 pairs of electrons, but always in pairs. Okay, good there? All right. Today, what we find out, we take a look at. When we have 2 atoms that are sharing electrons, we find out that it is not always a nice, even sharing. There is a property of atoms that we refer to as electronegativity. Electronegativity, as defined up on the board, says is the ability of an atom to attract electrons to itself when joined to another atom in a chemical bond. Electronegativity is, again, if we're personifying an atom, is the ability of an atom to share nicely with other atoms. What we find out is that some atoms are better at sharing nicely than others. A guy named Linus Pauling took all the factors that affect the electronegativity of the atom, and he graded them. Kind of like in kindergarten, you didn't get really grades in like reading and math and science. You got grades in like how well you followed directions and how nicely you treated other people and stuff like that, right? This is the atom's grade in sharing. How well does it share? Scale runs from 0 to 4. 0 meaning that it doesn't want electrons. 4 meaning that it wants electrons more than anything else in the whole wide world. Okay? Good there? Got those? So, here, you don't have this picture, but just to examine, here's a periodic table. And instead of atomic numbers and average atomic masses, it has electronegativity values. What do you see about the trend in electronegativity values? How would we classify it? Andrew, go ahead.
It increases when you go left to right. So pretty much like the closer to the mole bands of electrons, like all all the higher numbers mean selfishness and the lower means sharing, correct?
Yes.
Okay.
So your most selfish atoms are going to be where on the periodic table?
To the right, and the most generous atoms are to the left.
Good. So the atoms to the right are the most selfish atoms. The most generous atoms are to the left, right? And that makes sense with our trend, because we said, what are these atoms trying to do to gain stable octets? How do these atoms gain stable octets? What do? They gain electrons, right? Whereas these atoms look to lose electrons, right? The higher the number, the more those atoms pull electrons towards it. So, when we look at a bond, we find out that the important factor that we have to look at is the difference between electronegativity values. Notice that phrase is in bold, it is underlined, and it is also in italics, right? You think it's kind of important? Yeah, it must be important. So we look at the difference between electronegativity values, right? We have to look at one atom versus the other. A bond exists between two atoms. We have to look at the value of one versus the value of the other. So here's what we find out. First, I'm going to put up this screen so I can only see part of this. If we take a look at the difference between those two values, and we see that that difference comes out to be greater than 1.7, we would classify that bond as ionic. If there is a large difference in electronegativity, one atom wants those electrons so much more than the other atom, basically it just takes them away, or the other atom just gives them away, right? So we have a complete transfer of electrons. On the other end of the spectrum, if our electronegativity differences are between 0 and 0.4, we would classify that bond as non-polar covalent. Non-polar covalent. And that means that those electrons, because it's covalent, right, those electrons are going to be shared. In this situation, those electrons are shared evenly because, based on the electronegativity values, there isn't one atom that wants those electrons more than the other atom. And then finally, the middle ground is something that we call polar covalent. Polar covalent bond means that the electrons are being shared but they are not being shared evenly. Example. I have an 8-year-old son and a 6-year-old daughter. They both like to play Angry Birds on the iPad. But my son likes to play Angry Birds more than my daughter. So his idea of sharing is he plays 6 boards of Angry Birds, then he lets his sister play 1 board of Angry Birds. Are they sharing?
Yes.
Yes. Are they sharing equally?
Yes.
No.
Yes.
Right? That's the idea of the polar covalent bond. Both of those atoms want electrons, but one wants them more than the other. The idea of polar, okay? We've discussed this word before, or it's come up, right? What if we talk about where has this word polar or pole come up? Magnets, right? And when we have a north pole and a south pole, right? They're separate from one another. If we look at something from a quote-unquote a social studies standpoint, there are certain issues out there in our society that we refer to as polarizing issues. Does anybody know what it means to say something is a polarizing issue? Yeah, polar bears are in danger. That's what it means. I'll give you an example. Abortion is a polarizing issue.
You're either like
You can argue it both ways.
it's on either extreme.
You're on either extreme, right? That you could argue it, but people feel strongly about it one way, and people feel strongly about it the other way, right? It is a polarizing issue. It separates people. When we talk about this idea of polarity within a bond, we're talking about separating electrons. So in a non-polar bond, right, some atoms have the same atoms have the similar attraction, where the atoms that are sharing will share nice and evenly. As a result, those electrons are nice and evenly distributed, and the bond is pretty much the same all around. If we looked at electron density or probability, where would be the highest probability of finding electrons in a non-polar covalent bond? Where would we have the highest probability of finding those electrons if they are being shared evenly? Well, if you're sharing something evenly, right, where do those electrons stay most of the time?
Middle.
Right in the middle. So if we were looking at the probability of finding electrons in a non-polar bond, right in between the two atoms. Okay? But, on the other hand, we have something that we call a polar covalent bond. Right? Sorry, did we get all of that or no?
Yeah.
Sorry. So when these atoms share electrons, they quote-unquote spend equal time around each atom. There is an even sharing of electrons. The probability of finding electrons exists right in between those two atoms. All right? Here's what I want you to do. Over the weekend, I want you to finish up this outline. The slides will be posted online. Finish filling it out so we can quickly talk about it on Monday. Sorry, Tuesday.